Welcome back to the deep dive. Today, we're going to do something a little bit, well, a little bit dangerous.
Really like the sound of that.
We are going to take the very foundation of how most of us were taught to understand electricity, and we are going to completely dismantle it.
Dangerous is absolutely the right word because, if you stick to those basic ideas from your first physics class, especially when you're designing high-speed electronics, you're not just going to be wrong.
You're going to fail.
You're going to fail. Your boards are going to fail. It's almost a guarantee.
And that's a heavy way to start, but let's be honest, we all have that mental image burned into our brains, right? The water analogy.
Of course. It's the first thing they teach you.
Yeah, voltage is the water pressure, the battery is the pump.
The wire is the pipe. And the current, the little electrons, that's the water flowing through the pipe. It's intuitive. It's comforting, even.
It is. It makes perfect sense when you're hooking up a 9-volt battery to a light bulb.
For that, it's fine. It works. But the moment you're dealing with signals that have fast edges, the moment you're designing a real printed circuit board, that analogy becomes a trap.
Exactly. And according to the research we have in front of us today, for the world of modern PCB design and EMI control, that analogy isn't just an oversimplification.
It's a lie.
It's an absolute lie.
And it's a destructive lie. It's the lie that directly causes electromagnetic interference, or EMI. Because if you think of a PCB trace as just a water pipe, and you assume all the important stuff, all the energy, is neatly contained inside that copper wire,
Then you're missing the entire picture.
you're designing boards that are going to scream noise, fail your compliance testing, and, probably glitch out whenever someone uses a microwave in the next room.
So that's really our mission for this deep dive. We're going to unlearn that water analogy. We're going to replace it with the actual mind-bending physics of how signals really propagate.
It's time to face the truth.
We're digging into the source material from mastering EMI control in PCB design, and we're focusing on the module that covers signal propagation. And we should say, this all comes from the EMC and EMI design course provided by Fresu Electronics.
Right, and the insights we're talking about, this whole framework, it really comes from Dario Fresu. He's a principal engineer and an EMI specialist, and what I love about his approach, the whole philosophy of the course, is that he doesn't just hand you a list of rules to follow.
No checklists.
No, he takes you all the way back to the first principles, to Maxwell, to Heaviside. He explains why the rules exist in the first place.
Because if you don't understand the why, the how is just memorization. It doesn't stick.
And you can't problem solve. You can't adapt.
Right. So let's really set the stakes here. Why does this matter so much? Why can't I just connect the dots on my schematic, route the traces, and call it a day?
Because we're not moving water anymore. That's the key. In high-speed design, we are guiding electromagnetic fields. That's a totally different job.
Guiding fields.
Yes. And if you don't understand how those fields move, how they behave, you can't possibly contain them. And EMI, at its heart, is just uncontained field energy. It's energy that escaped the board because the designer didn't understand the shape of the container.
We're going to get into some ideas today that, I'll be honest, when I was going through the source material, they really blew my mind. I mean, we're going to talk about why current can actually flow where it shouldn't be able to through the insulation, the literal plastic of the board.
Right through it.
And we're going to talk about this ghost current that manages to close the circuit loop before the signal has even reached the end of the line.
It sounds like magic. It really does. Or, some kind of quantum weirdness.
It does.
But it's just physics.
Yeah.
And it all starts with understanding what a PCB trace actually is. It starts with a transmission line.
Okay, let's start right there. If a PCB trace is not a water pipe, what is it?
A PCB trace is a transmission line. Full stop. Now, that's a term we throw around a lot in engineering, but we rarely, stop and really define it properly.
So unpack that for us. What does that mean in the real world on a board? What is a transmission line, really?
Okay, so a transmission line is a structure that is designed to transfer energy from point A to point B. But here's the critical part. It transfers that energy as contained electromagnetic fields.
The key word being structure.
Structure. It's not just a wire, it's an arrangement of conductors.
And this is exactly where the schematic lies to us, isn't it?
Oh, the schematic is the biggest liar in the room.
You look at the schematic, you see a single clean line connecting, say, a processor pin to a memory pin. And you think, okay, that's the connection, one wire.
Exactly. And that's what I call the single conductor fallacy. In the real world, the physical world of your PCB, you cannot have a transmission line with just one conductor. It is physically impossible.
You need at least two.
You need at least two, always. No exceptions.
Oh, what are the two?
Well, you have the conductor you're thinking about, the signal potential conductor. That's the copper trace you draw on the top layer of your board.
Okay, the wire.
The wire, right. But you also need the reference potential conductor. And usually, for good design, that's the solid ground plane directly underneath that trace.
But on the schematic, ground is just. It's a little symbol. It's just a triangle pointing down. It's implied.
And that implication, that symbol, is why so many layouts fail EMI testing. Because the designer focuses 100% of their brainpower on routing that top trace nicely, making sure it's the right length, and they spend 0% of their attention on the return path, the conductor underneath.
But physics doesn't care about our schematic symbols.
Physics sees the reality. It sees two conductors acting together as a single system.
In the course material, Dario Fresu uses this analogy that I found really, really helpful. He talks about a container.
Yes, the container analogy is perfect. Think of the transmission line as a container for that electromagnetic field we talked about.
Okay.
The trace on top is the ceiling of the container. The ground plane on the bottom is the floor, the field, the energy. It exists and travels in the space between them.
So as long as you have a ceiling and a floor.
The field is contained, it's happy, it travels neatly from the source, point A, all the way to the load, point B.
Okay, so let's break it. What happens if I remove the floor? What if I'm routing this trace and I have to cross over a gap or a split in the ground plane underneath?
You've just broken the container. It's like trying to carry water in a bucket that has no bottom. What happens?
The water spills everywhere.
It spills everywhere, and on a PCB, when you lose that reference plane, the electromagnetic fields are no longer tightly bound between those two conductors. They have to expand, they balloon out, looking for a reference, any reference, to return to the source.
And when those fields expand and balloon out into the surrounding space.
We give that a name. We call it radiated emissions.
That's the thing that the antenna in the EMC lab picks up.
That is the energy reaching the antenna, and that is you failing your multi-$1,000 certification test. Uncontained fields equal EMI. I mean, it's that direct of a relationship.
So step one in our recovery from the water analogy is this. Stop seeing wires.
Stop seeing wires.
Start seeing structures. Start seeing these containers made of two conductors.
Precisely. You are never, ever just routing a wire. You are always, with every click of the mouse, constructing a tunnel for fields. And you have to build the whole tunnel, not just the ceiling.
Okay, this is a perfect transition then. Because this leads us to the part that I think is the biggest shock to the system for people who haven't, spent their weekends reading Maxwell's equations.
Right.
We've established we have a structure, we have a trace, and we have a plane. The big question is, where is the signal?
And if you asked the average person, or honestly even a lot of very experienced engineers who haven't gone deep into this stuff, they'll point right at the copper trace.
Of course.
They'll say, the signal is inside the copper, the electrons are flowing through the metal. That's where it is.
And the source material is very, very clear on this point. It says that is fundamentally wrong.
It's not just a little wrong, it's 100% incorrect. The signal is not inside the conductor.
Okay, I want to pause on that for a second because it feels so completely counterintuitive. We spent all this money on copper foil. We plate it with gold. We worry about the resistance and the thickness of the trace. And now you're telling me the signal isn't even in there.
The signal, and by that I mean the electromagnetic energy that actually carries the information, the ones and the zeros, that energy lives in the space between the conductors.
Space.
It lives in the dielectric.
The dielectric, so the FR4. The green stuff, the plastic and fiberglass material that we usually just think of as the mechanical substrate that holds everything together.
That's the beautiful irony of it. We call it the insulator.
Yeah.
We think its only job is to, keep the copper layers from shorting out. But in high-speed design, the dielectric is the medium of transport. It's the highway.
So let's go back to analogies. If the water analogy is a lie, we need a better one.
We do.
How should we picture this?
Okay, think of the copper traces. Both the top trace and the bottom plane. Think of them as the guardrails on a highway.
Guardrails on a highway. Okay, I like that.
And the dielectric, the FR4 or whatever material you're using, that is the pavement of the highway. The energy, which you can think of as the car, it drives on the pavement and travels through the dielectric. The copper guardrails are just there to guide the field, to keep the car from driving off the road and into the ditch.
That clicks. That makes so much sense. And it immediately explains why the material properties of the board matter so much for high-speed signals.
Exactly. I mean, think about it. If the signal was really inside the copper, then the type of plastic you put around it shouldn't really matter for speed,
It
right?
should be irrelevant, just insulation.
But it matters immensely. The source material talks about the propagation speed.
The speed of light, right.
Well, sort of.
Mhm.
The signal travels as an electromagnetic wave. In a perfect vacuum, it travels at the speed of light, little c. But when that wave travels through a material, any material, it slows down.
Okay.
It travels at the speed of light inside that specific dielectric.
So the insulator is literally setting the speed limit for your data.
Yes. The speed is determined by a property called the dielectric constant of the material. A material with a high dielectric constant is like trying to drive a car through thick mud. It slows the wave down. A low dielectric constant is like driving on fresh, smooth asphalt.
And this is definitive proof. The only way the material could affect the speed is if the energy is traveling through the material.
It's the smoking gun. The energy is in the material, not the metal.
This completely shifts your whole perspective on layout. You're not building a system of copper wires. You're building a system of dielectric waveguides. The copper is just the boundary condition.
Now you're thinking like an EMI expert. That's the mindset. You stop obsessing over the conductors and you start paying very close attention to the spaces.
Okay, so let's zoom in on this signal, this wave of energy that's traveling through the dielectric. In the digital world, we're so used to thinking in binary. It's a 0 or it's a 1, it's low or it's high.
But physics is analog. Nature doesn't do instantaneous. Nothing is ever just a 0 or a 1. There is always a transition.
Right, that transition takes time, the rise time or the fall time. And the source material focuses really heavily on this specific transition point. It calls it the wave front.
The wavefront. This is an absolutely critical concept to get. Imagine you've got a long transmission line on your board. At the driver end, the chip, you flip the switch. You go from 0 volts up to, say, 3.3 volts.
Okay, a logic high.
That change from low to high doesn't appear at the receiver chip at the other end of the line instantly. It has to travel.
It's limited by that speed we just talked about, the speed of light in the dielectric.
Exactly. So at any given moment, there's a specific point on that line, the wavefront, where the signal is actively changing.
You could think of it like a tsunami wave moving across the ocean.
That's a great analogy. Ahead of the wave, the water is calm, the voltage is 0. Behind the wave, the water is high, the voltage is 3.3 volts. But right at the face of the wave, that vertical wall of water, that's where all the action is.
That's the edge.
That's the signal edge. And physically, in terms of fields, that is the specific zone where the electric field and the magnetic field are changing explosively fast.
So why does the source material say this edge, this wavefront, is the dangerous part? Why don't we care as much about the steady 3.3 volts that comes after it?
Because of a fundamental rule of physics. Static fields, so a steady DC voltage, they don't radiate energy, they're stable.
Okay.
But changing fields do, and the faster they change, the more violently they want to radiate to escape into the environment.
This connects directly to that concept of energy compression.
Yes. Think about the rise time of the signal. If you have a slow, old signal, that energy transition from low to high might be spread out over many nanoseconds. It's a gentle sloping hill.
Right.
But in modern chips, we're talking DDR memory, PCIe, fast USB, the rise times are incredibly fast. We're talking hundreds of picoseconds, maybe even less.
So you're compressing that entire voltage change into a tiny, tiny sliver of time.
You're creating a vertical wall of energy. In engineering terms, you're creating a very high dVdt, a massive change in voltage over a tiny change in time. And that sharp edge, that wall, contains extremely high frequency energy.
Even if the clock speed of the signal isn't that high.
This is one of the most common misconceptions in the industry. People will say, oh, my board is only running a 100 megahertz clock. I don't need to worry about high-speed design rules.
Right, because 100 megahertz doesn't sound that fast anymore.
But it has nothing to do with the clock frequency. It has everything to do with the edge rate. If the edge rate of your 100 megahertz signal is, say, 500 picoseconds, then you have significant frequency content up into the gigahertz range, all packed into that rising edge.
So the danger of EMI, the thing that radiates, it lives in the sharpness of the edge.
The wavefront is the tip of the spear. As that sharp edge propagates down the dielectric, it is actively testing the integrity of your container, of your transmission line. If there is any weakness, a gap in the ground plane, a poorly designed via transition, that high-frequency energy at the edge is the first thing that's going to leak out.
Okay, so we have this wavefront, this tip of the spear, moving down the line. And this brings us to what feels like the absolute paradox of the whole circuit. The current loop.
Ah, yes, the current loop. This is where the water in a pipe analogy finally dies a very painful but necessary death.
Okay, let's set up the paradox for everyone. We all learned Kirchhoff's current law. For current to flow, you need a closed loop,
Yeah.
a complete circle.
Right. From the source, through the trace to the load, through the load to the ground, and then back to the source on the return path.
No loop, no current. Simple. Simple. We just established that the signal takes time to travel down the line.
We did. It's not instantaneous.
So picture this. Our wavefront is halfway down the board. It has left the driver chip, but it has not reached the receiver chip yet.
Okay, it's in the middle of its journey.
So physically, there is no connection to the load. The circuit is open at the far end. There is no complete loop back to the source.
From a classical DC circuit perspective, you are 100% correct. It is an open circuit.
But current is flowing. We know it is. The driver chip is actively pumping energy into the line. The wavefront is moving forward. How on earth can current be flowing if the loop isn't closed? How does the driver even know to send current if it hasn't connected to anything yet?
This is the question that, if you only think like a plumber, it will keep you up at night. It makes no sense. If you put a cap on the end of a pipe, water doesn't flow. But here, the current flows long before it ever hits the cap.
So what's the answer? Is Kirchhoff's law wrong?
Kirchhoff isn't wrong. He's just incomplete for this situation. He describes part of the picture. To get the whole story, we have to go to James Clerk Maxwell. We need to find the missing link that closes the loop locally, right at the wavefront, before it ever reaches the load.
And the source material from Fresu Electronics identifies this missing link very clearly. It's called displacement current.
Displacement current. This is the concept that saves all of physics. It's the term Maxwell himself had to add to fix a mathematical hole in Ampere's law. It's beautiful, really.
Okay, let's break this down because displacement current sounds like something out of a sci-fi movie. It sounds like technobabble.
Yeah.
What is it physically?
The best way to understand it is to forget the PCB for a second and just look at a simple capacitor. Two metal plates separated by an insulator, a dielectric gap.
Okay, got it.
We all know that DC current cannot flow through a capacitor, right? The electrons flow, they hit the first plate, and they just pile up. They can't physically jump across the insulating gap.
Right. For DC, it's an open circuit.
But we also know that if you apply an AC signal, a changing voltage, to a capacitor, it looks like current is flowing right through it. We use capacitors to pass AC signals and block DC all the time.
So something is happening in that gap.
Uh-huh.
But we just said electrons can't jump across. So what is moving?
The charges inside the insulation material are moving.
Inside the insulation. But it's an insulator.
It is.
Yeah.
So inside the dielectric material, you have all these atoms and molecules. They have positive and negative charges in them, but they are bound charges. They're stuck in the molecular structure of the material. They can't flow freely like electrons in a copper wire.
So they're locked in place.
They're locked in place, but they aren't frozen solid. They can wiggle, they can stretch and rotate.
They can wiggle.
Yes. When you apply an electric field across those two capacitor plates, all those little bound charges inside the dielectric, they polarize. The positive bits of the molecules get pulled slightly one way, and the negative bits get pulled slightly the other way. They all align with the field.
Like millions of tiny compass needles all snapping to point north.
That's a perfect analogy. Now imagine the electric field is changing rapidly, it's getting stronger, or it's flipping back and forth. What are all those little compass needles doing?
They're constantly wiggling back and forth, trying to realign with the changing field.
And that physical movement, that displacement of charge, even though it's just a tiny wiggle, that counts as a current. To the universe, a moving charge is a current. Maxwell called this displacement current. It is the current that appears to flow through the dielectric whenever the electric field is changing.
Okay, so that's the capacitor. Now let's bring it back to the PCB trace.
A transmission line is a capacitor. It's just a very long, skinny, distributed capacitor. You have the top plate, which is the trace. You have the bottom plate, which is the ground plane. And you have the dielectric, the FR4, in between.
I see exactly where this is going now.
As our wavefront, that sharp signal edge, travels down the line, what does it represent? It represents a massive, rapid change in the electric field in that specific spot.
A very high dV/dt.
And wherever you have a changing electric field in a dielectric,
You have displacement current.
you have displacement current.
So right at the tip of the spear, at the wavefront.
Right at the wavefront, current is literally blasting vertically through the FR4 insulation. It flows from the top trace straight down through the plastic and connects to the ground plane underneath.
That's the ghost current. That is how the loop closes itself.
It creates a local, instantaneous loop. The conventional current goes out the trace, dives down through the dielectric as displacement current right at the wavefront, and then comes back on the ground plane as conventional current again. It doesn't need to wait to reach the load. The loop travels along with the wave.
That's actually beautiful. It's so elegant. It solves the paradox completely.
It does. And understanding this three-part structure is the absolute key to practical EMI control. The source material breaks this down into three distinct components that all move together. And I think if a designer can visualize these three parts, they're halfway to solving most of their EMI problems.
Okay, let's walk through them one by one. The three components of this moving loop.
Component number one is the one we always think about. Forward current. This is the normal conduction current, the flow of electrons on the top conductor, the trace moving from the source towards the load.
Okay, standard stuff.
Component number two, return current. This is the conduction current flowing on the bottom conductor, the reference plane, moving back towards the source, equally important.
The path back home.
And then component number three, the magic link. Displacement current, this is the bridge. It flows vertically through the dielectric, connecting the forward current on top to the return current on the bottom, but only right at the signal edge.
So you have this complete self-contained loop structure that's just propagating down the board.
Exactly. I want you to imagine a hula hoop.
A hula hoop.
Yes. Picture a hula hoop that's rolling down the length of your transmission line. The very top of that rolling hoop is the forward current on the trace. The very bottom of the hoop is the return current on the plane underneath. And the front curve of the hoop, the part that's constantly diving down and touching the ground as it rolls forward, that's the displacement current.
The hula hoop rolling down the trace. That is a fantastic mental model. I'm going to use that.
And that visualization tells you everything you need to know about why the return path is so non-negotiably critical. For that hula hoop to roll smoothly and stay small and contained, the bottom part of the loop must be directly underneath the top part. It needs to be a tight, clean circle.
So what happens if it's not? What if I'm routing and I hit a slot in my ground plane? The trace continues over the top, but the plane underneath is gone for a centimeter.
You've just broken the bottom of the hula hoop. The return current can't follow directly underneath anymore. It has to find a different way back. It has to take a long, winding detour around the edge of that slot.
So the loop gets stretched out. It's not a tight circle anymore.
It gets massively deformed. Instead of a tight little circle, you've now created a big gaping loop area. And in the world of physics and EMI, a large loop area is literally the textbook definition of an antenna.
Loop area equals antenna.
The bigger the loop, the more efficiently it radiates energy. The bigger the loop, the more efficiently it picks up incoming noise. When you force that return current to detour, you are expanding the loop, you are breaking the containment, and you are actively, intentionally broadcasting that high-frequency edge noise to the world.
So the displacement current is trying its best to close the loop locally, but if we mess up the return path geometry, the whole structure fails and the energy spills out.
Yes. The displacement current will always try to form the bridge, but if the other side of the bridge is a mile away, the field has to stretch and expand to get there. And that's your radiation. That is why we say if you break the return path, you break the loop's containment.
Yeah.
You have just turned your beautiful transmission line into a very ugly and very effective radiator.
And what about the dielectric itself? Does the quality of the pavement matter for the hula hoop?
Oh, absolutely. The displacement current is the physical interaction with the dielectric material. If your board material is inconsistent, if it has a different dielectric constant in different places, or if you have air voids in the laminate from cheap manufacturing, you disrupt the displacement current. You make the loop wobbly, if you will. This can cause impedance discontinuities and signal integrity issues.
This just keeps reinforcing the same idea over and over. The empty space on the board, the insulator, is actually the most active, most critical part of the high-speed circuit.
It is where the magic happens, and it's where the danger lives.
And this brings us right back to the core philosophy that Dario Friasu teaches in the Mastering EMI Control course. It's all about controlling EMI at the source.
Right. And, there are fundamentally two ways to handle EMI in product design. There's the Band-Aid method, and there's the source method.
The Band-Aid method is what I imagine most people end up doing, shielding.
Exactly. You design the PCB poorly, you don't think about these field containment principles, it radiates like a cell tower, and then you try to fix it at the end by wrapping the whole product in a big heavy metal box. Or you start sticking ferret beads and conductive tape everywhere trying to plug the leaks.
It's expensive, it adds weight and complexity, and it's a nightmare for manufacturing.
It's a sign of failure, is what it is. It means the problem wasn't solved on the board. The source method is the opposite.
Which is,
You design the geometry of the PCB, the stack up, the trace routing, the return paths, so that the fields never want to leave in the first place. You carefully manage the forward, the return, and the displacement currents, so they always form a tight, contained loop. If the field is happy and comfortable inside the dielectric, it has no reason to radiate out into the world.
sounds like good EMI design is really just good high-speed digital design.
It is. They are one and the same. And here's the beautiful trifecta that the source material points out. If you do this, if you manage these currents and contain these fields properly on the board, you get 3 incredible benefits for free.
Okay, lay them on us.
Benefit number 1. Low electromagnetic emissions. This is the obvious one. You contain the fields, you don't radiate noise, you pass your compliance test on the first try.
Which saves a ton of money and time. Nice.
Benefit number 2. Low susceptibility. This is the other side of the coin. If your loops are small and tight, they are bad at radiating energy out, but they are also bad at receiving energy from the outside. Your board becomes naturally immune to external noise.
So it won't crash when someone keys up a walkie-talkie nearby.
Exactly. And benefit number 3,
What's the third one?
improved signal integrity.
Ah, SI.
Think about it. If energy is radiating away from your trace as EMI, that is, by definition, energy that didn't reach the receiver, you lost signal strength. You degraded your signal. By containing the field perfectly, you ensure that the maximum amount of energy gets from the driver to the receiver. So solving for EMI almost always fixes your signal integrity problems automatically.
It's amazing how this all connects. It all boils down to geometry and physics. It's not black magic. It's not a dark art.
It's always Maxwell. We just need to stop ignoring him.
So let's just wrap this up by summarizing the whole journey we've taken in this deep dive. We started with a lie.
The water analogy, please throw it in the trash.
We replaced that with the transmission line concept.
Yeah.
Structure made of at least 2 conductors.
The trace and the reference, the ceiling and the floor, the container.
Then we learned that the signal, the actual energy, is a wave traveling through the dielectric, not electrons flowing in the wire.
It's guided by the copper, but it's driving on the plastic.
We identified the wavefront, that fast signal edge, as the really dangerous spot where all the high-frequency energy is compressed.
The tip of the spear, the thing that tests your design.
And finally, we solved the mystery of how current can flow in an open loop by introducing displacement current.
The vertical bridge.
Yeah.
The ghost current through the insulation that closes the loop instantly and allows that hula hoop to roll down the line.
It really is a complete fundamental shift in mindset.
It is. And I'll tell you, once you start to see a PCB this way, you can't unsee it. When I look at a layout in a CAD tool now, I don't just see green lines on a black background. I see volumes. I see these 3D spaces where the fields need to flow cleanly.
And that actually leads me perfectly into our closing thought for you, the listener. I want to give you a challenge. The next time you open your CAD tool, whether it's Altium, Cadence, KiCad, whatever you use, don't look at the copper traces as wires connecting dots on a schematic.
Right, don't look at the lines.
Look at the spaces. Look at the gaps between the trace and the plane underneath it. That so-called empty space is actually your most critical component. That's where the signal lives. That's where the magic happens.
And ask yourself the question for every single critical trace. Did I build a good container for this field? Is there a clear, uninterrupted path for the displacement current to bridge the gap? Or did I leave the lid off the box?
Did I leave the lid off? That is the question that saves you from a 6-week delay and a $10,000 respin of your board.
Absolutely.
Now, obviously, we have covered a lot of deep theory here today, but this really is just the foundation. Knowing the physics is one thing, but applying it to a complex 12-layer board with thousands of nets, differential pairs, and multiple power planes, that's a whole other level.
Yes, it is. This deep dive was based on just one of the introductory modules from the Mastering EMI Control curriculum. The full course goes much, much deeper into the practical how-to.
So if you're an engineer, a PCB layout designer, or just someone who is, frankly, tired of chasing down mysterious EMI failures, you should really check out the full resource.
It's the Fresu Electronics Academy. Dario Fresu has built an entire program that takes these fundamental concepts and translates them directly into practical, repeatable strategies for first-pass success.
You can find it all at freezuelectronics.com. If you want to stop guessing and really start mastering the fields, that is the place to go.
Stop plumbing, start engineering.
I love that. That's the perfect way to end it. Stop plumbing, start engineering. Thank you for listening to this deep dive.
Look at the spaces, everyone.
And mind the return path.
Always mind the return path.